The next topic we're going to be looking at is kind of a foundational topic in algebra. It's called linear functions. And basically what we're going to be looking at are equations that represent a line graphically. Okay, it's kind of neat how these, how the algebra of an equation and the graph of a line interrelate to each other. Okay, so here's just an overview, and I'm going to spend not a lot of time going into the detail or deriving formulas. It's really just going to be a brief overview so that you can practically use these things and convert from an equation to a graph or a graph to an equation as needed relatively quickly. Okay, so just an example here, a linear function or a linear equation is any equation that has two variables, but they're each raised to the 1 power, right? So there's no squaring. It's not like x squared or anything like that. It's just x and y. Okay, nice relationship there. And so an equation that has two variables, the solutions are ordered pairs. So you're looking for a value for x, a value for y, pairs of values that when together make the equation true, right? And there's a lot of them, okay? In fact, there's an infinite number of them. And so in this particular example, x plus 2y equals 7, I could pick out a value for one of the variables and figure out what the other one would have to be in order to make it work. For instance, if I let the x value, if x is equal to 3, then you could just plug in a 3 and figure out what the y would have to be to make that equation true. In other words, to make the left side equal to the 7 on the right side, make them the same. And so you solve, subtract off the 3, 2y is equal to 4, divide both sides by 2, and then y is equal to 2. So your ordered pair then is the combination of those two. So the solution is the ordered pair 3, 2. It's a pair of numbers and in a particular order. The order specifically is x and y. So we always do the x first, the y second. Now the variables could be different. They don't have to be x and y. But typically in mathematics we're going to use x and y. It's kind of a standard notation. Although if you're doing this in an application, if those variables are supposed to represent something specifically, then you might change the letters, right? We've seen them before. You could do something like the Fahrenheit to Celsius conversion is a linear function where you use f and c as the two variables. And so the variables are arbitrary. We're just going to use x and y as the two for our purposes. So anyway, the solution is the 0.32 here. But there are many other ones. In fact, any combination, and you think about it, you plug a 3 in here, you get 3, you plug a 2 in here, this term is 4. So 3 plus 2 times 2, which is 4, is 7. But I could choose any combination, right? I could do the number 1 for x, and that would be a 1 here. So this would have to be a 3. The y would have to be a 3 times 2, which is 6. So 1 plus 6 gives me 7. And to make this 6, the y would have to be 3. So 1 comma 3 is a solution. And I could make up a whole bunch of these. I could do a 0 for the y value, right? If I plug something in for the y value, what plus 0 gives me 7? Well, 7 does. So the x would have to be 7. And I can, I can just play around with the numbers a little bit, or I can do a little bit more work to solve them if it gets confusing, if I'm not really sure how that plays out. But what's going to be interesting is if I plot these points on an axis or on a plane where I have two axes. One axis or one number line is what we call the x-axis or the horizontal number line, and the other is the y-axis or what we call the vertical number line. So we usually set up the x horizontally and the y vertically as standard notation. And these are number lines, so it's like a ruler with all the numbers, all the real numbers stretched out in each direction. And so what we can do is plot them. They intersect at the origin, so that origin there is 0, 0, 0 in both directions. That's not actually a point on the line though, I'm just noting that. But if I wanted to plot these, I could do, let's see, 1, 2, 3, 4, 5, 6, 7, 8. I'm just kind of plotting some units here, some tick marks, so I know roughly where I'm going to be putting these. Trying to keep my spacing relatively consistent. And so each of these little tick marks I'm going to consider 1 unit. Okay, and I'm not going to write everything in, but just so you can kind of see. Positives go right and up, negatives go left and down. And so 3, 2 is a point 3 units over, 2 units up. So you go right 3, that's in the x direction, up 2, that's in the y direction. And I have a point there at 3, 2. 1, 3 is a point, so I go over 1, up, over to 1, and up to 3. 7, 0, so if I go out to 7, there's a point there, 7 and up 0, okay, 7, 0. And so I can, what you'll notice, if I did this enough, and maybe with these 3 you can even see it, but if I did this enough, you'll notice they all line up. They're all going to line up. Not only are all of the solutions going to line up, but every point on the line that connects them will be a solution to this equation. And so I can sketch a line, and this line continues indefinitely in both directions. So I could put really big numbers in for x, I could put really small numbers in for y, or big numbers for y, it doesn't matter. I can even put decimals and fractions in. That's why I fill it in completely and I'm not just putting a bunch of dots, because every number, every real number can be plugged in for x and you can find a corresponding y. So every point on the line, connected line, is going to be a solution to that equation, okay? So that's kind of your overview of what a linear function is. It's a 2-variable equation where the variables, where the solutions are ordered pairs, and when I plot those solutions on a set of axes like this, I get a line that represents a graphical line, okay? Straight line. Now, one of the more common forms of a line is the standard form. That's what this equation is in. We're going to have the variables on one side, a constant on the other. The variables have coefficients a and b. Those are just numerical multipliers. So the coefficient of x here is 1, because technically it's 1x. So that's your a is 1. The coefficient on y is 2, so that's like your b value there is 2. And the constant, the 7, is your c. All right, so that's a standard form. This is a good example of a standard form. What we're going to see are some other types of forms of equations that you're going to be looking at. One of them is called the slope form. Now what's interesting about a line is that it has a constant rate of change. In other words, if you were to increase your function by 1 in the horizontal direction, it's going to have a certain rise or increase or decrease vertically, okay? If you were to increase again by 1, it's going to have, the exact same increase or decrease as the first time. And so for every fixed horizontal change, the vertical change will be the same every time, okay? And because it's going to be fixed, we call that, we give it a name. It's called the slope. The slope is the ratio between that fixed, the fixed rise or vertical change divided by the fixed horizontal change, okay? So, and this is true for between any 2 points. So, and there's some geometry that goes into deriving this in terms of looking at similar triangles and proving that no matter what 2 points you use, the ratio between the vertical and horizontal sides are always going to be the same. And so what we end up with is this idea that the slope is defined as the rise in the graph divided by the run between any 2 points. It has to be specifically for 2 points. And so if I took, one point over here on the left and a point over here on the right, and I calculated the vertical distance between them, the horizontal distance between them, and divide the vertical divided by the horizontal, I'm going to get a certain value called the slope. And if I change one of the points or change both the points and do the same calculation, it's always going to come out to the same value, same slope, okay? So as a result of this, we can construct this formula called the slope form. And the slope form really just gives you, it just takes arbitrary points. So obviously for any line, you need 2 points, right? If I just had 1 point, there's an infinite number of lines that run through 1 point. As soon as I introduce a second point, it fixes our lines to just one option. There's only one possible line that goes through 2 points. There's no other option than that, okay? And so if I arbitrarily or, not arbitrarily, it's not the word, generally label these, boy, my handwriting is bad here. Label these points as, they're both x, y coordinates, but I'm going to distinguish them by calling them x1, comma, y1, and x2, comma, y2. That just distinguishes between the x value and the y value. And so, I'm sorry, between the two x's and between the two y's. And so, if I want to calculate the slope, which is the rise over the run between those 2 points, I need to calculate, if I think about a right triangle here, the rise, which is the vertical change of that triangle, vertical leg, and that's just the difference in the y values. We call it y2 minus y1. And the run, which is the horizontal side, and that's just the difference between the y values. We call it, or I'm sorry, the x values. Said that wrong. X2 minus x1, and that's our horizontal side. Okay, so this length, the run, is the difference between the x coordinates. Now this example over here, you might say it's the difference between 7 and 1 if those were the 2 points that you were looking at, okay? And that would be a run of 6, right? The difference between 7 and 1. So you just subtract them. Vertically, same 2 points, the difference between 0 and 3, okay? So you subtract, 3 minus 0, you get 3. So it's the rise divided by the run. It's a ratio, rise to run. And the slope, we usually use the letter M to represent slope. Don't know why. We just do. That's the letter. And so the slope form is nice, and you can pick any 2 points you want, plug them into that formula. In this particular example, let's say I wanted to do 3, 2 and 1, 3. If I were to pick those 2 points, I'll label them x1, y1, and x2, y2. It actually doesn't matter which one's which, as long as we're consistent when we plug them in. So here I would say that the slope M is equal to y2 minus y1. So that would be 3, because that's the y2, minus 2, which is the y1. And then on the bottom I have x2 minus x1. Correspondingly, that's going to be 1 minus 3. Okay, so I just plug in the 4 numbers. They have to be in the right spot. And then you calculate. Numerator, that's a difference of 1. 3 minus 2. Denominator, 1 minus 3 is negative 2. 1 divided by negative 2, if I want to simplify that fraction, is simply a negative 1/2. Okay, or negative 0.5, but decimals aren't very useful here. And so what that means is that the negative means it's a drop, okay? The graph is dropping. That makes sense. So it's a negative 1, so that means it's a drop of 1, and 2 is a run of 2. That means you're dropping 1 and going right 2, and that gets you to another point. And that'll always get you to another point. No matter where you start, if you drop 1, run 2, run meaning moving forward, drop 1, go to the right 2, you'll get to another point on the graph, okay? No matter where you start. All right, so now we can put this together, and we can do this for any pair of points on any line. You can get the slope using this formula.